let's also look at the half loaded gain with RL, no RS this time. So one of the two, but this one being present is RL this time. And this is V out over V in. But V out where there's RL basically, with RL connected. We should emphasize on that because on the output side, the generated amplified by open loop gain, of course, of Vi is shared between an output impedance R out is sharing an RL and a load resistance RL, which is now connected. Now it is there. So V out is there. So in that situation, AVO VI, which is the total voltage, by voltage divider, multiplied by RL, therefore, over RL plus R out should therefore give V out with RL connected basically. So we are talking here about V out with RL connected divided by VI, which is the gain we are looking for, the half loaded with RL, should be obtained by moving VI this side and dividing it this side. So you get the open loop gain that we know the formula of times RL over RL plus R out. Similarly to having RS, we also having RL here, creating a loading parameter, which is also less than 1 because it's RL divided by RL plus something. And the fact that this is less, this part only is less than 1, not the whole thing. The fact that it's less than 1, multiplying something less than 1 by AVU reduces it. So AVU is still higher, therefore, than the half loaded gain with RL, no RS. Okay. But this is what we call the output loading factor. RL over RL plus R out that we can calculate is the output loading factor, and it has to always be a number less than 1. So now, the last category, the third type of gain, which is the fully loaded gain that we sometimes use for the symbol GV or sometimes AV fully loaded. So where there is, it simply means RL is connected as well as RS. Both the load resistance and the source resistance are present in it. So that is computed as V out over Vs, but V out with RL, of course. And that is, as you could have guessed, is the AVO multiplied by the input loading factor multiplied by the output loading factor. Input loading factor capturing the impact of RS presence, and output loading factor capturing the impact of RL presence. So at the end of it, that will be minus GMR out over 1 plus GMRE1. What is our input loading factor? Our input loading factor is R in over R in plus RS multiplied by, what is our output loading factor? RL over RL plus R out. If we replace R in and R out by their values, we end up with R out by the minus GMRC in parallel of RO divided by 1 plus GMRE1. All of it multiplied by R in, which is, we know it's RB1 in parallel of RB2 in parallel of R pi plus beta plus 1 RE1. All of that divided by RB1 in parallel of RB2 parallel of R pi plus beta plus 1 RE1. All of this plus RS, of course. The other side we've got RL, which is RL plus R out, which is RC in parallel with the small R out. But that's a very extended formula. Normally one would use that one. Or you just compute that alone. You compute that separate, that's separate, and you multiply all three. So that's how you get the fully loaded gain. And that concludes this first sub-configuration of common emitter. There are other types of common emitter sub-configurations before we go on to common base and so on. There are some other types of common emitter that we are yet to exhaust. and we are moving to the next one, which is we title in the notes. In the notes, we are calling it one moment. That new method, we calling it sorry. The next common emitter configuration is what we call